Hi everyone and welcome to the fourth video of this series. I ended the last video by talking about the Meissner effect in superconductors, and to begin this video I'm going to talk about a superconductor that is in the shape of a ring. So what we basically do is we apply a magnetic field and we use induction to initiate a current in the ring, and then we wait until the current has stabilized. So what does it mean for the current to be stabilized? What it essentially means is that a steady state has been reached. So next, I can write the magnetic field as the curl of the vector potential. And so if I now integrate around a closed loop around the ring, as you can see in the picture. So this is the closed loop, and S is the area that that is formed by this loop. So now if I use Stokes theorem, so using Stokes theorem, I can write the left hand side of this equation as follows. And to repeat, S is the surface enclosed by the closed curve C. Now I want you to recall a very special equation from the previous video. I'll write it down now. I'm going to use this equation and substitute it uh, in this equality here, this equality. I want you to look at this equation here, and particularly the right hand side of this equation. Now you might think, by looking at the right hand side, that since this is a closed loop integral of the gradient of some quantity, hence it must be equal to 0. However, this is not the case here. Actually, this turns out to be a multiple of 2 pi. And if you're thinking, how is that the case? So this can be understood in terms of uh, the phase of the wave function. So recall that uh, I had written psi as the under root of rho times some phase exponential to some phase factor. So if I integrate around a loop, it won't make a difference if this theta, it acquires some multiple of pi. So if, for instance, it acquires 2 pi or perhaps 4 pi. If I integrate around the loop, then uh, this exponential won't change at all. So it is actually valid if I write the right hand side as the integral on the right hand side as some integer multiple of 2 pi. So I should mention that n is an integer. Further, uh, I'm going to assume that the path is completely inside the bulk of the superconductor. So just to recall, this is the figure which I drew at the beginning of this video. So I'm assuming that the path goes completely inside the bulk of the superconductor. Now next, I'm going to use the Meissner effect to imply something very important. So the Meissner effect, because of the Meissner effect, the interior of the superconductor will have zero magnetic field, which means that the current density inside the bulk of the superconductor is actually zero, and Js is present only on the surface of the superconductor. Now, this is a very important observation. Next, what I'm going to do is I'm going to write this underlined equation again, and I'm going to point out something important. Now we have just stated that Js is zero inside the superconductor. And so what this means is this term goes to zero. This term is actually zero. And what we are left with is the integral of the magnetic field around the surface is equal to this quantity on the right hand side. And you may quickly recognize what the left hand side is. This is nothing but the magnetic flux through the superconducting ring. And what we have just proved is that the magnetic flux is quantized. And the flux actually equals 2n pi times h bar over q. This is an important result, and I will end the video now. In the next video, we will begin with a new topic, that is the Josephson effect. See you guys in the next video.